Hello everyone. In this lesson we are going to find bending stress on a beam that is under loading. You see a beam here with the loading conditions shown and the dimensions shown. You can see the dimensions of the cross section of the beam. So if this is XY plane, this is YZ plane. So you look at the beam from the side and the cross section is like this. The first thing, when we say bending stress, we usually are interested in the maximum bending stress, because when you reach the maximum, the material will fail from the maximum point of stress. Okay, the first thing we are going to do is to find the maximum moment. And you remember from the shear moment diagrams, we first start with the global free body diagram of the beam, and then we draw a shear diagram and then moment diagram. On the moment diagram we can see the maximum moment. Let's draw global free body diagram first. So I free up from this fixed support and show all the external loadings. I have got reaction force in this direction. I can say Ry, and also I will have a reaction moment, and let's call it Mr, reaction moment. In order to find them, we write free body equilibrium equations. What should we start with first? If I write vertical force equilibrium equation, I do it here. So Ry is equal to 3.6 kilonewton. What about the moment? So I take moment about this point equal to 0. Mr is in positive direction. 2 kilonewton rotates the beam around this point in the direction of clockwise direction, so it is negative. 2 times 20 centimeters, I write it 0.2 meters. .6 kilonewton also rotates it in negative direction, and it is 0.5 meters. We also have got 3 kilonewton external moment, and it is in negative direction as well, equal to 0. From here Mr is equal to 3 plus this one is 0.8, this one is 0.4. Mr is equal to 4.2 kilonewton meters. So I have found all the unknown reaction loadings, reaction force and moment. This one is 4.2 kilonewton meter. So from here I can proceed to the shear diagram. So on the x-axis we have this distance, on the y-axis we have got V, and the unit is, let's say, kilonewton. as given here. So how do I start? I see that there is an external load 3.6, so I go up by 3.6. Here's 3.6 on the V diagram. I go from 0 to 3.6, and then till the next discontinuity, which is this. By the way, we have got 3 discontinuities in this beam. 1, 2, 3. This one is the beginning of the beam. It is a discontinuity. This one is where the point load is applied. Second discontinuity, and this one is the end of the beam, also a point load, a place for the where point load applied. Third discontinuity. So between each discontinuity, the load is internal shear load is constant. So if I am 3.6 here, I will continue as it is. Here I come across with 2, and I go down by 2. So what will it be then? 1.6. If I go down by 2, it will be 1.6. 3.6 minus 2, 1.6. So from the second discontinuity to the third discontinuity, there is nothing else in between, therefore it is constant till the next discontinuity. I came here and I see that there is a downward force, and therefore I go down by the same amount. So the diagram is closed, therefore it is correct. So shear diagram is complete. Next, moment diagram. Again, we put the discontinuities. We plot the discontinuities and then start with the values. There is MR here, 4.2 kN. It is in positive direction, but it causes negative direction internally. Therefore, we start from negative 4.2. It is moment. The unit is kilonewton meter. 4.2 minus 4.2. From here to here, from the first discontinuity to the second discontinuity, how will I go? I look at the shear diagram and I see that the 3.6 times 0.2 meters, what does it make? 3.6 times 0.2, 0.72 kilonewton meter. So it is positive. So we will add up 0.72 here and go to the next discontinuity. But how will we go? Will we go straight, or will it be a slope or a hyperbola? It will be a slope. It will be a linear increase, because the sections I plot here, they are equal size. Therefore, it will be a slope here. From 4.2, if we add if we add positive 0.72 onto minus 4.2, what do we get? We get minus 3.48. So the moment in this point, at this point, will be minus 3.48. It is a slope. It is a linear increase from minus 4.2 to minus 3.48, because at each unit distance, the size of the sections are the same. Therefore, it is a linear increase. Here I'm at this point, and from this point to the third discontinuity, what will be the moment? Again, I look at this the area here. What is it? It is 1.6 times 0.3. So this one was 3.6 times 0.2 meters. This one will be 1.6 times 0.3, this area. Again, the size of these sections are equal to each other for every unit distance. Okay, 1.6 times 0.3, what does it equal to? 0.48. So this is positive 0.48. Therefore, I will go up, my moment value will increase by 0.48. Therefore, on the third discontinuity, my moment value will be minus 3. Okay. And then I see there is a moment, external moment at the tip of the beam, and it is in, when we look from outside, it is in negative direction, but it is causing a positive moment internally. Therefore, we go up by 3, and the diagram becomes a closed loop. So when we look at this moment diagram, we can easily see that the maximum moment is minus 4.2 kilonewton. So M max is equal to minus 4.2 kilonewton meter. Now I want to find what the maximum bending stress is. Maximum bending stress. Why do I want to find this? Because if this beam is going to fail by a normal force, by a normal stress, it will fail from this point, from where the maximum moment is. Now, you might remember that the maximum bending stress is equal to maximum bending stress is equal to moment times C divided by area moment of inertia. Moment, we know what moment is. C is the distance from the centroid or from the neutral axis to the point of interest, and I is the area moment of inertia of the cross section. And C, for C, we will choose the distance, the biggest distance from the centroid, from the neutral axis to the outside of the cross section. It will either be here or here. Okay. Now I know this. I will calculate this after I find the centroid, and after finding the centroid I will need to find the moment of inertia. Okay, therefore I need to find the neutral axis, the centroid of the cross section. Okay, I'll keep this paper for now and find the neutral axis of the cross section. If our beam had a cross section like this, we can easily say that the centroid is this. So if the beam had a cross section with a height of say 50 centimeter or 50 millimeters, the neutral axis would be here, 25 millimeters above the bottom of the beam. bottom of the section. 25. But our section, our cross section, is not a rectangular shape, it is a T shape. It is a T shape. Therefore, it will be closer, slightly closer to this shape. I mean, it will deviate from this line towards this rectangle, so it will be somewhere around here. Our neutral axis, in other words, our centroid will be around here. So how do we find the centroid? There is a formula for this. Say if this is y bar is equal to summation of the areas times their distance to this point divided by summation of the areas. You may forget this. After you complete this module, you may forget this formula. It looks easy, but it is normal that you forget it. In order for you not to forget it, I will show you an example. So this is our cross section. This is another one, they are the same cross sections. And I hold it like this, okay? I choose one of them and hold like this. You know that with the weight this body has, it is trying to rotate downward like this. It has got a moment. It is applying a moment on my fingers. It is very lightweight, of course, but if it was a heavy object, it would be a bit difficult for me to hold, for my fingers to hold it in place. So it is applying a moment, you know that. And how do you calculate this moment? You have got two options. One is to know the centroid of this object. If the centroid of this object is given to you, like say this is the centroid, what you are going to do in order to find the moment. By the way, we don't deal with this. What you do in order to find the moment, you multiply this distance, the force arm, this is force arm, say D, by the weight of this object, the weight of the whole object, say this is W. By doing so, you calculate the moment that this object applies on my finger. This is one way. Another way is same cross section. Another way is to divide it into two pieces. Assume it as two pieces like this. Okay, two pieces hold together. Assume two pieces here, and we know that the cross sections, as I plot here, as I shown, and the distance would be, let's draw it here, and for this is W1, this is W2, and the distance of, so we want to find the moment. What is the moment? This is, say, D1, and this one D2. Therefore, the moment of these two pieces apply on my fingers are D1 times W1 plus D2 times W2. So these are equal to each other. That means dW is equal to di wi, right? We have got these indices. So from here, you can say summation of di wi divided by w. So the w is the weight of the whole structure. So if you compare these two equations to each other, you will see that they are quite similar. And this is what we call moment, or in other words, moment of a force. This one is moment of area, or first moment of area. So if you multiply area by the distance of the centroid of the area to any point, you find first moment of area. This is moment of force. This one is moment of force. This one is moment of area. So if you happen to forget this equation, just remember this one and make an analogy. You will remember how to find the centroid of a body, of a simple structure like this. Okay, using this equation we find the centroid first, and that will give us the neutral axis. Once we find the neutral axis, we will find the area moment of inertia, which is the I, capital I, and the C. From them, C and I, using these we will find the maximum bending stress. Okay, so y bar is equal to y1. So we can, so let's draw it here again. So our dimensions was 50 here, these are in millimeters, and 10. There are two rectangles simply, and the dimensions are 10 by 50 in millimeters. So assume this line like a moment, where the moment is applied. So in this, as I shown in this example, and we find moment of area. So y1 times a1 plus y2 times a2 divided by the whole area. So what is y1? If this one is rectangle 1, this is rectangle 2. y1 is we do it in millimeters. We will convert it into meters later on. So y1 is 25. This is y1. The distance from the centroid of the rectangle to the line of interest. This is my line of interest, and I chose it. Usually it is chosen at the bottom of the shape. y1 25 times area is 50 times 10 and 500 area a1 plus y2 is 50 plus this is y2. Let's show it here. y2 is equal to 50 plus 10 over 2, the half of the height of this rectangle. So it is equal to 55, right? 55 for y2 times a2 is equal to 500 and divided by the whole area, which is 1000. So from here we get, let me calculate it, 25 times 500 plus 55 times 500 divided by 1000, so it is 40. Y bar is equal to 40 millimeters. So the neutral axis of this section is here. So neutral axis, what is it? We shown before. It is where the section is rotating around, or you remember we shown that bending, so normal forces, normal force or normal stress on the section of a beam which is under loading. If it was a straight beam with a cross section like this, if it had a rectangular cross section like this, the stress distribution or normal force distribution would be something like this. You remember? And this is where the normal stress or normal load is 0. This is neutral axis. This one was for a straight rectangle. But we have got a T-shaped cross section, and neutral axis here will be here 40 millimeters away from the bottom. So we will calculate the area moment of inertia according to this, and also the parameter C according to this centroid. Okay, next we calculate the bending stresses at the top and bottom of the section. We know that the maximum normal loads or normal stresses will happen at the ends, at the top or bottom of the section. So if we want to draw a normal stress distribution on this section, say this is how you look at the section now. If we rotate it like this, if you look from this side and draw it, the stress distribution will be something like this. This is where the normal stress is 0. Okay, let's calculate area moment of inertia, which is also called second moment of area. So what is the formula for area moment of inertia? I was equal to BH cubed over 12 plus D times D squared times A. So you can say D or Y for this term, and it is the distance between the centroid of the chosen area and the centroid of the whole section. Okay, our cross section, let's keep it here. So we will do this for each rectangle. You know, this is the centroid of the T shape, 40 millimeters away from the bottom line. And each rectangle has its own centroid. So I is equal to I of the whole shape is equal to summation of let's say I1 time plus I2. So what is I1? I1 is equal to, if this is the rectangle 1, this is 2. I1 is equal to, where's our dimensions? B is 10, this one, 10 times H is 50, this is H, and it's 50, 50 cubed or 12 plus d. What is d? D is here, distance between centroid of the area of interest. This is the area of interest, the area 1, centroid of this area, distance between this point and the centroid of the whole shape. So this is d1. And what is it? It is 40 minus 25. d1 is equal to 40 minus 25 because this is 25. Therefore it is 15 squared times a, which is 500. So what is it equal to? 10 times 50 cubed 12 plus 500 times. It is okay, we can convert this is in millimeters, millimeter to the power 4. We can convert it into meters, or should we keep it this way? For now, keep it this way. Calculate I2. I2 is equal to B for I2 is 50. This is B for the area 2. 50 times 10 cubed. This is the height of the area 2. Divided by 12 plus. What is D2? D2 is this. So again, the distance between the area of interest, centroid of the area of interest, and the centroid of the whole shape. This is the centroid of the whole shape, and this is the centroid of the area of interest. This is the distance d2. And what is it? How do you find it? There is 10 here. We can just do d2 is equal to the whole height is 50 plus 10 minus is the whole height of the shape minus 40 minus half of this distance, half of the height of area 2, which is 10 over 2. From here, 60 minus 40, 20, 20 minus 5, 15. D2 is equal to 15 millimeters. So millimeters. Okay. Again, 15 squared 500 for the area of the rectangle 2. What do we get? We get 116,666.67 millimeters to the power 4. Okay, we have found the I1 and I2. If you sum them, we get the whole area moment of inertia of the cross section plus 216. So, okay, it is I is equal to lots of threes. Okay. So what was our formula for the bending stress? MC m times c over I. So if we want to find the maximum, we will give the maximum c, because moment and I are same for the whole section. It doesn't change, but c changes within the section. So if this was our centroid and we want to find this bending stress at this point, the c will be this. So if I want to find bending moment at bending stress at this point, my c will be this distance between the point of interest and the centroid. So what is the highest c I can give? It is this or this. The distance between centroid and the top of the section is 20, right? So from here to here it is 20, but from here to the bottom it is 40. Therefore the largest c I can give is 40. So sigma bending max will be m max times c max divided by I. This is small letter c. It's not capital letter, this is small letter. So what was m max? We found 4.2 kilonewton meters. It doesn't matter it is minus or plus. 4.2 kilonewtons. It is in meters, kilonewton meter, and now I made it newton meters, and I want to convert it to millimeter. So another 10 to the power 3. So now this became newton millimeter. Times C max was 40, this is millimeter, divided by 333,300. Okay. And it is millimeter to the power 4. Now if you calculate that, 40 divided by times I get 504 newtons. So this is the maximum normal stress that can occur in under this loading condition. Under this loading condition, this is the maximum normal stress that we can get. By looking at this value, we can make sure if the structure is safe or not. If this exceeds yield stress, then the structure is not safe under such kind of loading. Okay, if we draw the profile of the stress distribution, so where is this stress? It is at the bottom of the section, so draw it here. So this is our section. We look at it from the side, and the neutral axis here, 40 mm from the bottom of the section, and we know that this is happening at the bottom of the section, and we know that the moment is negative, therefore there is this kind of moment applied, internal moment applied at this section. Therefore the bottom of the below the neutral axis there is compression, because so this is support, fixed support, this is loading. So what's happening is the bottom portion is compressed, and we know from this moment diagram there is a negative moment, and it means the moment direction of the moment is like this, therefore there is a compression at the bottom. And the maximum is 504 Newton. So here there will be tension, but we don't know the maximum tension value, maximum tension stress. In order to calculate this, we do maximum for tension. So again, Mmax times C, for C it is 20 divided by, again, same I. When you calculate that, you will find the maximum tension stress, and it is from here. The only value that is changed is C, therefore it is half, and therefore the maximum tension stress, normal tension stress is 252 Newton tension, maximum tension stress, maximum compression stress 504 Newton, and in total absolute maximum normal stress is 504 Newtons. Right, thank you for listening. This is the end of the bending chapter, and we'll see in transverse shear chapter.